What happens to the mind after death? This age-old question, often approached through religious or philosophical lenses, has recently gained attention from an entirely different direction: information theory and physics. Could the self, the conscious experience you call you, be an emergent information structure that might, in theory, persist beyond biological death? To understand this idea, let's first explore what the brain really is from a physical and informational standpoint. Your brain is not a static object. It is a dynamic, self-organizing network of roughly 86 billion neurons, each forming thousands of synaptic connections. Together, they generate a constantly changing pattern of electrical activity, chemical gradients, and information flows. Over time, this pattern gives rise to memory, perception, emotion, and consciousness. Some neuroscientists describe the self as a process, not a place, a continuously updated algorithm rather than a fixed object. So here's the first question. Is your mind just what your brain does, or is it a pattern that could, in principle, be preserved or recreated? This brings us to the idea that the mind might be an emergent structure of information. According to this view, consciousness emerges not from any single neuron, but from the organization of the whole system. The way information is stored, transmitted, and transformed, in the same way that a tornado is not a thing, but a pattern in the atmosphere, yourself might be a pattern in the brain's energy and information dynamics. If that is the case, it is theoretically possible, though incredibly complex, to model, preserve, or perhaps even reinstantiate that pattern. Could such a pattern persist after death? Well, biologically, when the brain dies, the pattern collapses, neuronal activity stops, memories degrade, and the coherent structure dissolves. But in the same way that digital information can survive the destruction of one storage medium, a hard drive, say, if it's copied elsewhere, some have speculated whether it might be possible to preserve a human mind's informational structure digitally. This is the dream of mind uploading, a science fiction concept under active discussion in fields like transhumanism and theoretical neuroscience. But is there any scientific pathway toward that? Current neuroscience is nowhere near mapping all the synapses in a human brain, let alone simulating consciousness. Projects like the Human Connectome Project or Blue Brain Project aim to reconstruct portions of the brain in silico, but we are far from recreating a human personality. Still, the idea opens the possibility that the self might be more informational than strictly biological. Some researchers in physics like Max Tegmark go further and suggest that consciousness might be a state of matter, an organized flow of information that obeys certain physical laws. Another fascinating idea involves black hole information paradoxes and the holographic principle, which suggests that information is never truly lost in the universe, even if a system is destroyed. Could this apply to consciousness? The analogy is loose, but tantalizing. If consciousness is a physical process and physical information is never erased, might some echo of you remain in the fabric of space-time? Of course, all this remains speculative. No one has ever recovered a personality from a decayed brain. But these thought experiments force us to reframe the question of the afterlife from mystical terms to computational ones. It's not where does the soul go, but can the information pattern of a mind persist, be copied, or be reactivated? If so, what would it mean for our ideas of identity, death, and continuity? So could there be an afterlife as an information problem? Only if the mind is truly an information pattern and if future physics, neuroscience, and computing can find a way to preserve or emulate that pattern. Until then, the question remains open, not just to philosophy, but to science itself. The human mind is widely regarded as an emergent phenomenon arising from the complex information processing of neurons. It is not localized to a single neuron or synapse, but is distributed across dynamic patterns of electrical and chemical activity. These patterns encode perception, memory, identity, and consciousness through recursive loops and feedback. As an emergent system, the mind is more than the sum of its parts, suggesting it may follow principles similar to those in complexity theory. Information, not just matter, becomes the key substrate for subjective experience. This raises the possibility that the continuity of self may depend on the persistence of organized information structures. Brain organoids in laboratories show spontaneous electrical activity resembling sleep patterns, hinting at mind-like emergent behavior, like a melody that exists in the arrangement of notes, not the instrument. Consciousness may depend on pattern, not flesh. Claude Shannon's information theory provides a mathematical basis for encoding, transmitting, and preserving information. Applied to the brain, this implies that thoughts and memories are representable as configurations of information patterns. If such patterns could be preserved or replicated, the mind could theoretically be copied or reinstantiated. Some theories propose that neural correlates of consciousness correspond to stable attractor states in high-dimensional information space. This leads to a view where the mind is not destroyed by death, but rather its information can, under special conditions, be retained or reconstructed. The fidelity of memory and identity preservation becomes a central technical and philosophical challenge. Neural connectome projects aim to map the brain's complete wiring diagram, hoping to preserve thought patterns for future modeling. Like backing up software on a hard drive, what matters is the code, not the device running it. Some speculative models, such as those proposed in quantum consciousness theories, suggest that information underlying consciousness may be stored in entangled quantum states. These states are inherently non-local, meaning that the information might not be confined strictly to the brain. If identity is partially encoded in quantum correlations, then part of the self might persist beyond bodily death, at least temporarily. While such models are controversial and lack empirical confirmation, they offer a framework where mind could be partially substrate-independent. The challenge lies in proving whether quantum entanglement has any functional role in long-term memory or selfhood. The Penrose-Hameroff-Orcher theory posits that consciousness arises from quantum computations in microtubules, like a hologram encoded in light interference patterns. The image persists even when the physical surface changes. In digital physics and simulation theory, the universe may itself be a computation, with consciousness arising as software-like processes within a physical substrate. If this is true, then it may be possible in principle to back up, simulate, or even reboot consciousness in digital environments. Several research programs explore mind uploading, neural prosthetics, and brain-computer interfaces, aiming to one day simulate subjective awareness. If successful, this would offer a form of digital afterlife where mind persists in a non-biological domain. However, the philosophical issue of whether simulated minds are real selves or merely functional imitations remains unresolved. Tech companies like Neuralink are working on direct brain-shaped interfaces that could one day store neural data indefinitely, like saving your personality into a virtual world. Your character may live on, but is it still you? According to classical thermodynamics, physical systems evolve toward entropy, suggesting that death brings irreversible informational decay. However, modern physics, especially in black hole thermodynamics and quantum mechanics, posits that information may be fundamentally conserved. If so, then even the information that constitutes a human mind might not be lost, but instead dispersed or encoded in inaccessible ways. The question becomes whether such information is truly annihilated or simply transformed beyond retrieval. The entropy of death may be informational noise rather than erasure, challenging our assumptions about the finality of biological life. Hawking radiation initially seemed to erase black hole information, but newer theories suggest this information is preserved on event horizons, like ink dissolving in water, hard to recover but not destroyed. Pan-computationalism is the idea that all physical systems perform computations, and that cognition can, in theory, arise from any substrate capable of processing information. If true, consciousness does not require a brain specifically. It could emerge from silicon, networks, or even exotic materials, provided the processing architecture is sufficient. This underpins the notion that post-biological consciousness might emerge in AI or uploaded format. The challenge is defining what organizational structure is essential for consciousness to reappear. This gives philosophical backing to the idea that mind may survive death via continuity of pattern, not matter. AI agents like GPT-4 show emergent behavior with minimal hard coding, suggesting that pattern organization trumps physical composition. Like playing chess on wood, stone, or touchscreen, the game remains the same across platforms. Near-death experiences report vivid sensations, memories, and even perceptions of consciousness outside the body. Neuroscience studies show that the dying brain may enter a hypersynchronous state where information integration spikes just before complete shutdown. This may create the illusion of an ongoing or disembodied consciousness. Even when vital signs are minimal, such findings suggest that the brain may momentarily amplify information before total loss, offering clues to how the self winds down. Whether this reflects residual biological activity or taps into deeper informational processes remains debated. EEG readings during cardiac arrest show a surge in high-frequency brain activity just prior to flatline, like a candle flaring up right before it goes out. The final burst may seem like a new beginning. Memory engrams are physical traces of memory encoded in specific neuron groups. If these patterns could be precisely mapped and replicated, identity reconstruction might be feasible even after death. However, memory alone may not suffice. Continuity of subjective experience and personality integration may require more than data. Still, understanding engram stability and transferability is central to the idea of informational persistence. The boundaries between storage, self-awareness, and consciousness blur as engram studies advance. Optogenetics can activate specific memory engrams in mice, triggering behaviors linked to specific experiences. Like restoring a saved game, you can revisit the state, but the original player may no longer be holding the controller. Even if the persistence of mind as information were technically feasible, ethical dilemmas remain. Who owns the information of a deceased mind? Is a recreated consciousness a continuation or a copy? These questions challenge definitions of personhood, death, and rights in a future where identity might be stored, transferred, or multiplied. Philosophers and ethicists must wrestle with whether preserving information is equivalent to preserving a self. The afterlife may become less a spiritual belief and more an engineering problem with profound implications. The Digital Immortality Institute is exploring laws for data inheritance and posthumous digital rights. Like cloning a book from its text file, the words survive, but is it still the author's voice?